Okay, no question.
We didn't hear anything you said before, so maybe that's the question. What did you say in the past 6 minutes?
Yeah. Oh. Okay, so I already have to splice it in. So I'll splice it in. Yeah. Okay, so we were going over. We force charges onto the top plate. Because of those charges on the top plate, we force the like charges off the bottom, and we end up with a separation of charges. And because of that separation of charges, you can think of a constant electric field being generated or persisting between those two plates. As long as you keep those charges separated, that electric field will persist. And I think I gave you, yeah, excuse me, I think I might have the animations off here. Just to give you an idea, for this type of arrangement, I said that the magnitude of the electric field between the two plates is given by the density of the charges, the surface charge density, charge per unit area of the plates divided by a constant, the permittivity of free space. And then I went off onto, hey, this is related to light, and the reason that permittivity of free space is important, and yada, yada, yada. Backtracking, here's another question I have for you. The electric field between the plates is constant. What will the electric potential lines look like? If I wanted to plot out the equipotential lines between the capacitor plates, what should I draw? What should they look like? What should I draw? Yeah, draw it in real fast. Draw it in real fast. Yeah. Talk to your neighbor, get an idea. What do these things look like? Draw them in. Take a guess. It doesn't have to be right. Justify it if you can. Made me sad. I got one justification from my astronomy class of I Googled it. Don't Google it. All right, take a stab at it yourself. Life goes on. Did you get your ears lowered?
No.
You did it? Okay. It looks like you have your ears lowered. No? You didn't get a haircut? Oh, okay. It looks like your ears are lowered. Maybe that's just me. Okay. Nobody else got their ears lowered. I mean, I did, but I was like, did you get your ears lowered? Yeah, did it hurt?
Yeah.
Yeah, I hate it when they paste them back on. It's tough. No? Yeah. You got an idea? And really, the underlying idea I should ask, I'll ask this: how do I relate the electric potential to the electric field? Or in other words, if I have the electric potential, how do I get the electric field? The strength of the electric field, the magnitude. The battery's good for exactly one class. Yeah, go ahead.
Isn't the equipotential line perpendicular to the electric field?
Okay, good. So the lines of the equipotential lines are perpendicular to the electric field. So that gives you an idea already about how the electric potential lines should be drawn. Okay, good. Okay, so So we know they should be horizontal. The electric field is perpendicular to the equipotentials. So we know that they should be a horizontal line. I agree. Okay. What about spacing? Yeah.
I think they'll get closer together when it's closer to the plates.
Okay, so let's see if I can draw that here. So you're saying, okay, it should be closer together. And then I'll draw a third one here just because I'm not much of an artist. I already broke my little thing to do, Bob. Sorry. Pretend I have it. Didn't take long. I guess I'm just too brutal with stuff in my bag. Let's say the rest of you.
I thought perpendicular mean that they'd be vertical.
Oh, perpendicular to the vertical lines. So you'd have to go that way. Right, yeah. So if I drew these on the same graph, then yeah, I'd do perpendicular to the direction of the electric field. Let's say the rest of you about the spacing. Should I draw them closer together the closer I am to the plate?
I thought it would be they're closer together when they're like equidistant, like right in the middle, they'd be closer together and they'd go like get farther apart as they get closer.
Oh, okay, so one is, okay, closer to the plate and they get spaced out, and the other one is they're close together in the middle, and then they space out as I get further away. Okay, so we've got a couple of ideas. Let's say the rest of you. Are we voting somebody off the island, or are we? Yeah. And it comes back to, how do we estimate the magnitude of the electric field based on the electric potential?
The change in electric potential?
The change in electric potential, otherwise known as, I should say, the change in electric potential as you move some distance. Right, we said, hey, the electric field, the magnitude, is the change in the electric potential as we change distance. I'll use y here. Otherwise known as the slope. Right? The slope of the electric potential gives us the magnitude of the electric field. So the electric field is constant. Right, over here, the electric field is a constant value. So that means the slope of the electric potential is constant. So if I'm drawing equipotential lines, how do I represent a constant change? If I'm thinking equipotential lines. They're the same distance between each line. They are not closer together, close to the plate, and as they spread out, it doesn't start close together in the center and spread out. No, they're constant the whole way through. In other words, okay, so we'll strike this from our memory. They're constant. Right? The distance between the equipotential stays the same. Again, that's for the parallel plate capacitor. Yes?
Can you explain that one more time, why it's constant?
Yeah. So the electric field, the magnitude of the electric field is given by the slope of the electric potential. We have a constant electric field. That means the slope of the electric potential is constant. And how we represent a constant slope, if we're thinking topographical maps, is that the spacing between the lines stays the same. Yeah.
I think what I'm a little confused on is, how do we know that it's a constant electric field? Is it because the capacity of the permittance is in the denominator, or how exactly do we know?
Yeah, how do we know that? One way to think about it. So I gave a heuristic argument. I didn't do the whole derivation or anything, which is beyond the scope of the course. But the heuristic argument would be something like, let me consider just these two charges on the top plate for a second. Okay. So if I have the left charge and I have the neighboring charge, the right one, and the electric field due to the left one should go outwards. Right? It's a positive charge, so I should draw the electric field lines emanating from that positive charge. Next to it, I have another positive charge. And I'll do this one in blue, I guess, some other color, so hopefully we can see a contrast. So this one, again, the same idea. I should draw, although I'm having trouble drawing straight lines, and I should draw them emanating away from the second charge. If I look at, say, a field point right here, What can you tell me about the horizontal components of the electric field from those two source charges?
I mean, what they like cancel each other out.
They cancel each other out. The horizontal components will cancel. What do the vertical components do?
Not a dipole, but that's one that you think of, like, down.
Yeah, it's going down, they add.
Yeah.
Yeah. So that would be at least the heuristic argument that, hey, the electric field has no horizontal components, they're just vertical. Okay. Then the other piece comes in is that if I make this thing infinitely large, if I make this plate really, really large, then it doesn't matter where I'm located, I'll see the same electric field.
Okay.
And then I stop there and I say, okay, no, we'll just use that idea.
Okay. And is that hold true with all capacitors? Like, will it always be a constant electric field?
Technically, no. Okay. So this is a result that applies for parallel plate capacitors. Okay. Now, usually we think of that as being two parallel plates as large as you want. Okay. But there are other types of capacitors. There are what's called spherical capacitors, where instead of having flat sheets, you have two spheres, one embedded inside the other. Or there's one that's called a cylindrical capacitor, two coaxial cylinders. Beyond the scope of this course. For the purposes of this course, we will just deal with parallel plate capacitors and call it good. Okay. Yeah, no, I removed the capacitor assignment completely. So there was one time I had a spherical capacitor, but I think I removed it completely because it's in the capacitor assignment and I don't have that assigned here. I'll double check. There's one problem I'm worried about, and the reason I'm thinking about it was because it was supposed to model a cell. So it was a spherical capacitor instead of a parallel plate capacitor. But I think I give you the equation for it, but I'll double check it. Yeah. Yes.
Can you describe again the difference between electric field and electric potential? There's no voltage to change in potential.
Yeah. So we'll try this. Right? The relationship between the electric field and the electric potential is the same relationship between force and potential energy. So if the relationship between force and potential energy is the same as between the electric field and the electric potential. I don't know if that helps. Yeah, the electric potential, another way to say it is the energy per unit charge.
So like to put that, like to visualize that, it basically be like a constant hill, like a ramp instead of like a hill that curves, or what's up on the.
Yeah, exactly.
Since it's a constant.
Yeah, you could think of this instead of having some kind of curved slope, it's a constant ramp. It's a straight ramp from one to the other. Yeah. Yeah, a constant slope. Yep, exactly. Other questions? Yeah, so parallel plate capacitors are nice because it is a way of establishing a constant electric field in a given region. Or if you prefer, you could think of it as constant, equally spaced equipotential lines. Which means the change in energy, if you're thinking about moving charges, say, from one plate to the other, one plate, excuse me, that should be a negative charge. But if you're thinking about moving charges from one plate to the other, each charge has the exact same change in potential. Which means if they're the same charge, they get the exact same change in potential energy. They cross the same number of equipotential lines. That means that they'll have the same change in energy, so long as they're the same charge. Or maybe I should say the change in energy of the charge will be proportional to the charge itself. Incidentally, usually when that happens, it's a bad thing. We can talk about that later, but that's called arcing. If charge jumps from one capacitor plate to the other, it's called arcing, and it usually ends up destroying the capacitor. Okay. It's like a miniature lightning bolt. I mean, that's what an arc is, right? In fact, you want to, miniature lightning bolt yourself, just rub your feet on the carpet and then touch the doorknob. Okay. So essentially what, yeah, okay. Yeah, okay. And I just, okay, I have that back in there, I wrote that down. Okay, so let's think about this for a second. I wanted to remind you, of course, then I take it off this slide as well. Don't forget the magnitude is the surface charge density over epsilon naught. So I thought, let's play around with this idea a little bit, just to kind of get an idea about what's going on here. And I like visualizing these equipotentials. So question for you. Let's say I take a capacitor and I charge it up. Now, I don't care how we charge it up. I'm just saying, hey, I've put separate charges on the top plate and the bottom plate. And then I'm going to disconnect it. So those charges are stuck on the top and the bottom plate. There's nowhere for them to go. And then let's say for a second that I take the two plates and I stretch them. So I have fixed charge on the plates, but then I stretch them to increase the area of the plates. The question I'm wondering about, number one, well, okay, let's just go here. What happens to the equipotential lines between the two plates? So I charge up the capacitors, I disconnect them so the charge has nowhere to go, and then I physically stretch the plates, make them larger in size. What happens to the equipotential lines between the two capacitor plates? Go ahead, talk to your neighbor, see if you can come up with an idea. Go. What happens to the lines? As I stretch this sucker.
Yeah, so you're
yeah, because you're essentially increasing, or excuse me, you're decreasing the charge density. Yep. So what does that mean about, you're making that number smaller, which means that's going to be smaller, so these vector lines should get shorter. What does that say about the spacing and vector potential?
Yeah. You got it? You got an idea?
Is it stretching the plate or making them further apart?
I'm sorry?
Is it stretching the plate or making the plates further apart?
It's stretching the plate, so it's increasing the area of the plates while maintaining the plate separation. So you're stretching them, but they stay the same distance apart. Yeah. Of course, what's stretching them going to do? Okay, so yeah, you're going all the way to the equipotential. I agree, it will change the distance between the equipotential lines. Yes. Will they increase or decrease in separation?
Increase?
They'll increase in separation. Yeah. I agree. Let's walk through. Well, how do you get that? Well, first of all, if I make the plates larger in area, what have I done to the surface charge density, the charge per unit area, if I increase the area? I've decreased it, right? I said there's a fixed amount of charge on there, right? It's very important I disconnect the battery or whatever I'm using to charge up these things. So if I increase the area, I have decreased the charge per area. Well, if I decrease the charge per unit area, this sigma, that number goes down. That means the magnitude of the electric field decreases, right? I should make them shorter. Sorry, I should. That's not quite overlapped. We'll work on that. I wish there was like a snap to grid type feature. I'm sure there is, but always snaps to the wrong location. Okay, so the magnitude of the electric field has decreased. What does that mean about the spacing of the equipotential lines? Steeper slope or less steep slope? And steeper slope is higher magnitude. Yeah, you had the right idea the first time. Yeah, you're good. Yeah. I'm sorry? A less steep slope, a smaller slope, which means the number of equipotential lines that I can draw between the two plates goes down. Okay? Larger spacing. And so as area goes up, sigma goes down, the magnitude goes down. Okay. Oh, shoot!
Wait, can you go back one more?
Yeah. Shoot, I asked the question verbally and then I have the slide actually asking the question. I apologize. Now, please bear in mind, this is if I had fixed charge, right? I dumped a certain amount on, I removed the source, so there's no way to add any more charges or to remove the charges. Okay. You get a different result if I kept the source, the battery still connected. Okay. So to be continued. And so for a fixed amount of charge, as I increase the area, the equipotential spacing increases. Electric field decreases, the equipotential spacing increases. Less steep slope, shallower slope.
But if you did the charge like attached,
Mm-hmm.
wouldn't the spacing from the potential lines get rid of them?
Yeah, let's see here. If I left the supply of charges attached, I mean, in reality, it's a battery. But if I left the supply attached, as I stretch the plates, it will maintain the same charge density. So if I increase the area, I'll increase the amount of charge that's on the plates, but the ratio, the charge density will stay constant. Mm-hmm. So that's why I gotta be careful. Yeah, so if I stretch the plates and leave the source attached, then you'll get the same spacing.
Okay.
Mm-hmm. Yeah. Now, if I unhook the battery and put a stronger battery in, then I can force more charge on, and that will decrease the spacing between the equipotential lines. So that's why it's always important to ask yourself, okay, is the source attached, is the supply of excess charges attached, or is it not attached? No. Other questions? Yeah, so I had this and then, okay, I messed it up. Survey says, just asking what I have. B, further apart. Okay, keep going. Yeah. Give me a B. I will give you a new term here. So we call this a parallel plate capacitor. And what we are going to define is a new physical quantity. Okay. Now, please bear in mind, this is just a straight out definition. Okay. I know some people have heard me say this before. There are two types of equal signs in physics. One of them is a straight out definition, and one of them is a relationship. And you're relating systems to surroundings, for example, interactions. Now, unfortunately, there's this triple equal sign that's supposed to be used to say, hey, this is a definition. Okay? Most people just use the regular equal sign. So, I mean, minor difference. So this is just a straight out definition. It is not giving you, let me give you an example. Equations I consider to be relationship equations. Newton's second law. It's giving you a relationship between the interactions with the surroundings and the response of the system. Or work kinetic energy. It's telling you the work done by the surroundings results in a response of the system, namely the increase in kinetic energy. That's a different type of equal sign than the force of gravity is defined as mg. Right? That's not giving you a relationship at that point. It's just telling you, hey, this is what we defined it as. Or kinetic energy is 1/2 mv squared. It's just a straight out definition. This one's a straight out definition. Okay. So C is what we call the capacitance. If you want to, I think I defined this in verbally. I said, hey, it's how much charge an object can store. I think is kind of how I said it. From a physics standpoint, we define it as the ratio between the stored charge and the difference in electric potential. A different way to say it is the capacitance is a constant of proportionality between the charge on the object and the change in potential between the plates. For every unit of charge I put onto this object, I get a set amount of change in potential. Linear. Right? So yeah,
Could you repeat what you said about the capacitance being a constant of proportionality between something and something?
Yeah, you could think of it as a constant of proportionality between the charge on the object and the change in electric potential. So it's in some ways it's just kind of rewriting this. So we could rewrite it as the charge that you place on the object divided by the capacitance tells you the potential difference between the two plates. So for every charge I dump on, for every charge I increase, I can tell you how much the potential has increased by. I did that right? Yeah, I just cross multiplied. So again, this could actually, if you wanted to say, well, experimentally, how would you do this? How would you find the capacitance of an object? You take the object, measure, take the object, put charge on it, a set amount of charge, and then just measure the potential difference between the two plates with your little mapping probe. Do it again, dump some more charge on, another amount of charge, do it again. Do it again, do it again, do it again. And yeah, the slope of the line will give you the capacitance of the object. You plot charge, the independent variable being like the charge deposited, the dependent variable being the potential difference between the plates, and then the slope of the line will tell you the capacitance. So of course the hard part is how do you dump a set amount of charge on? That's the issue. Yeah, how would you do that? You could hook up. Think about that a little more. You could hook up different batteries, and you could say that the charge deposited is. Yeah. I'll have to think about that a little more. But, yeah. The devil's in the details, right? Conceptually, you know how to do it. Now it's just a matter of how do we get that, set amount of charge that we put on. let's go ahead and get an expression for the potential, or let's get an expression for a parallel plate capacitor. Because the other thing I told you is that although it doesn't, in this form, it's not particularly apparent. But it turns out that the capacitance is, again, only related to the geometric properties of the capacitor. I think I affirmed that at the beginning. I said it will only depend on the area, the plate separation, for example. Geometric quantities, the physical shape of the object. But that doesn't look like it here. Right? If I say Q over delta V, the deposited charge divided by the change in potential between the plates, that doesn't look like it has anything to do with how the object is shaped. So let's go ahead and see if we can come up with an expression for the capacitance of a parallel plate capacitor that is based solely on the geometric properties. And we actually have everything that we need. We're just going to have to do a little bit of playing around with the equation. Okay, yeah. I can't remember here. Oh, no, I don't have it yet. Okay, do you want to do that first? I asked you, okay, you already have an idea. Yeah, let's see here. So we already talked about that if I fix charge and I stretch the plates, I decrease the number of equipotentials between the plates. Which means delta V has decreased. Q has stayed the same. Delta V has gone down. What happened to the capacitance? It increases. Right? My delta V, I'm dividing a number by a smaller number, the capacitance increases. A way to think about that is if I've increased the area of the plate, it has the ability to have more charge, store more charge. So conceptually, what I want to say is that we know that the capacitance should be proportional to the area. As I increase the area, the potential between the plates goes down. That means the capacitance goes up. There's more places for me to put the charge. If I supply more. I need to supply more charge first. Okay, yeah, now I got it, okay. Well, I wanted to jump to the end without going through the, right? You always want to checkmate the king before you take the knight. No, take the knight first, then checkmate the king. Don't jump all the way to the end. Amagater, right? Just got his millionth subscriber. Yeah. Let me tell you, chess is fascinating. It's one of those that I always wish I were better at, but I'm not.
You seem like his number one fan.
I'm sorry?
You seem like his number one fan.
I'm his number one fan. Okay. So let's play this game again, but we're going to do something different now. So here we go. Let's say I have set up my charged capacitor, and I've got some established electric field there. And I'm sorry?
I didn't get to pick up the last slide.
Oh. Say charge is is that the proportional that's similar? Shoot, maybe is the proportional like that alpha sign? Is that right?
Yeah.
Okay. The capacitance is proportional to A. Oh, and I should apologize. I don't make the rules, so be careful, right? Because now you have two C's associated with this class. You have C as in the capacitor, and you also have C as in coulombs, the unit. And so be aware. Unfortunately, both of those are used and they're both standard. So you're going to have to know from context. And it doesn't mean the unit C or does it mean capacitance C.
So the capacitance is increased.
No, I'm sorry?
So the capacitance is increased.
The capacitance is increased, yes. Sorry, slight byline. You notice here that the units of capacitance are a coulomb per volt. So I'll put the units in parentheses here. So the units of capacitance, you could say it's a coulomb per volt. Let's see, you could go further than that. You could say that it's a coulomb. A volt is a joule per coulomb. So you could say it's a coulomb squared per joule, which isn't particularly insightful. Shoot, what else could you call this? Well, we could break it down. We could break the joule down into smaller units if we want. Unfortunately, most of the time you won't see either of these. You'll see what's called a farad. Oh, sorry, I should write that in. A farad. And to give you an idea, most capacitors that you walk around or that you would see in everyday life are on the order of nano to microfarads. You might run across the millifarad every once in a while. Okay. So to give you like physical capacitors that you would see in everyday life are on the order of 10 to the negative third to 10 to the negative ninth. If you get a 10 farad capacitor, like, yeah, I think the largest I've seen is like 1 farad, and it's like the size of a hockey puck. Because again, the physical size of the capacitor will dictate how much it can store. So like a 1 farad capacitor is like a hockey puck size. And if you have like a 10 farad capacitor, that's going to be, like, I don't know how big, like, power plant kind of things. Okay. Oh yeah, anybody ever see like a computer backup power supply? Like you can buy these when there's a power outage. The battery, quote unquote, will power your computer instead. Like those things are like the size of a briefcase. Right? I think those have capacitors in them. I don't think they're actually. I'd have to double check. I think there's capacitors in them, not actual with batteries. Okay. The nice thing about capacitors is that they don't, like you don't have to worry about any chemical reactions. Right? You don't have to worry about degradation of the material. So yeah, farad. So next question, the next thing I want to consider. So now let's say we've set up our electric field, we've deposited charge, we have a constant surface charge density. So now what I'm going to do, rather than disconnecting the supply and stretching the plates, I'm going to disconnect the supply and just separate the plates, increase the separation. Okay. Now, although I don't have it visually represented here, I want even though I'm separating the plates, the separation distance is still smaller than the overall area of the plate. Okay. In other words, I want to ignore the fringe field. So, no, I didn't have it here because it's hard to make an infinitely large plate and yada, yada, yada. Okay. So, modeling. So I've deposited the charge, and now I will separate the two plates. And the question I have for you, after I separate these two plates, what can you tell me about the change in electric potential between the bottom and the top plate? Stays the same, increases, decreases. Go ahead, talk to your neighbor, get an idea. All right? If I take these two, charge it up, disconnect the supply, now stretch the plates far apart. Does it increase, decrease, or keep the electric potential the same? Oops. So,
So the spacing between is the same. Yeah. So again, the question comes down to, you have more money. If the spacing stays the same, you think about it, increase the place. Think about it. So you have more equitable lines or less.
Yeah, but you're right.
More. Yeah, the spacing stays the same, but now I have more. Wow, I just come here and you're just like, stop. Sheesh. I do record.
you got an idea?
Stays the same.
Okay, stays the same. So you're saying that there's the same number of equipotential lines between the plates. Is that right?
The distance between them stays the same.
Oh, no, I'm stretching the distance
Of the plates.
of the plates. Yeah. Yeah. Well, let me ask you this. The electric field, the strength of the electric field, does that change? I see some no's, I see some yeses. Yeah. I'll write it up here again. Sorry, I should just have it on every slide and I forgot. Right, the electric field, the magnitude is given by the surface charge density over epsilon naught. And the surface charge density, that depends on the charge and the area. Have I changed the amount of charge on the plates? No. Have I changed the area of the plates? No. So have I changed the charge density? No. Which means, what can you tell me about the magnitude of the electric field? It stays the same. So as I move these plates apart, the electric field between the plates stays the same. What can you tell me about the spacing of the equipotential lines if the electric field is constant? The lines stay constantly spaced. So the electric potential, the equipotentials are equally spaced, but now I've stretched the distance between the plates. Which means, do I have less equipotentials or more between the two plates now? I have more, right? There we go. I stretch it. The electric field stays the same, which means the spacing between my equipotentials stay the same, which means if I stretch the plates apart, I have more equipotentials between them. Yeah.
This might sound super dumb, but earlier you said the electric potential,
Uh-huh.
but that equation is like KQ over R. So
KQ.
if you're increasing R, then why would it increase? I thought it would decrease.
Yeah, no, this is a good question. You're right. The electric potential is given by KQ over R. Yeah. I should specify further. I don't remember if hopefully I specified this at some point. That equation is for a point charge.
Oh.
And here we're not dealing, unfortunately, with a point charge. We're dealing with a bunch of point charges. Yeah. So what happens is, because we're dealing with what's called a distributed charge, this result that we will get is if I took an infinite number of point charges and added all of their contributions together.
Okay.
Yeah. No, that's a really good question. That organization slide, like when I had Coulomb's force and I had the electric field, and then I had the potential energy and the electric potential, those all refer to point charges. Now, you already know what to do if you have more than one point charge. You use the principle of Superposition. You say, let me consider the contribution, the individual contributions from each source charge, and at the end of the day, I'll add them together.
Can you just give that explanation again of like how we know the equipotential number increases?
Yeah. We know that the electric field stays constant. Or okay, I'll start off at the top. Okay, the charge on the plate stays constant. I've disconnected the supply, and the area stays constant of the plates. So I have not changed the charge density on the plates. And so the magnitude of the electric field stays constant.
So it doesn't matter how far apart the two plates are?
Yeah. And practicality matters. I'm saying the plates are infinitely, I'm keeping the separation distance small relative to the area of the plate. From a practical, let me give you a different example here. Right now, you go outside and you look at the Earth. It looks like it is infinite. Right? You go outside, it looks like the Earth just stretches on into infinity. Why? Why does it appear to be like that? It has to do with your eyes and also the fact that you're standing on the surface of the Earth. Your eyes are only located about 2 meters above the surface of the Earth. What do you have to do in order for the Earth not to look infinite? You have to go higher, right? You have to pay Elon Musk. You hop onto one of his Dragon capsules. He launches you 400 miles into the air. And when you increase the distance above the surface of the Earth, all of a sudden this Earth that looks infinitely large, all of a sudden starts to look finite, starts to look round. That's kind of the same idea that's going on here. Okay? I want these plates close enough together so that if you're standing in between the plates, they look infinitely large. And I think I had that on the slide on Monday. I said I want the plate separation to be small compared to the area. That makes the plate, from the standpoint of anything inside, that makes the plates look like they're infinitely large. Yeah, so when I'm doing this procedure, I want to stretch it just for conceptual purposes, but I still want to make sure that they look infinitely large. So yeah, I'm not going to stretch it like 10 meters apart or anything like that. Does that kind of help? Yeah. Maybe, yes. Yeah, we could try it here, right? Like, hey, you want to make this table look infinitely large? Just get really close to the surface. Right? Oh yeah, this looks bigger already. Yeah.
So you're increasing the number of lines, that increases the delta V, right?
Correct. The difference in potential from the top plate to the bottom plate. Oh, we didn't finish the explanation. Okay, so the surface charge density stays the same. So the electric field strength stays the same. Right, sigma stays constant, if sigma is a constant, sigma divided by a constant is still a constant. So the electric field, the electric field is a constant. Well, that means if I stretch the plates apart, that means I still keep the same length of electric field arrows between the plates. And so the electric field stays constant. I just have more arrows, but they're same length. Well, that means, okay, so there's that. Then we say, well, if the electric field is constant between the two plates, that means the change in potential, the spacing between the equipotential lines stays constant. So if my spacing stays constant between equipotential lines, and I've increased the distance between the two plates, that means I have more equipotential lines between the two plates. And because I have more equipotential lines, that means I have a greater change from the top to the bottom plate. Or a different way to say it, I have the same slope, but a longer distance. So I'm going to have a larger change in height.
And then the distance between the equipotential lines are the same?
Yes.
The sign is too left.
Yep. Yeah, so I guess, yeah, the analogy would be, okay, well, you have a ramp that has a slope of, 30 degrees, and the length of that ramp is 5 feet. Then you go to another ramp, which has the same slope, but the distance is now 20 feet. Which ramp gives you a larger change in height? The 20-foot one, right? It's the same slope, but you have a longer distance that you can travel along the ramp. What happens to the capacitance? So if I set the charge it up, unhook it, I stretch it, I say now I have a larger change in potential between the bottom and the top plate. What can you tell me about the capacitance? It decreases. Yeah. So we have another idea here. Is that, okay, well, I have two ideas. Oh, I already said this. Okay, well, so we have an idea here. We said that the capacitance is proportional to the area. And we said that the capacitance is inversely proportional to the distance. As I increase the area, the surface charge density goes down. The spacing between the equipotentials increases, and I get a smaller change. Whereas if I increase the distance between the plates, I have more equipotential lines between the plates, and so the capacitance goes down. Now we just have to work out the little devilish details. We have kind of the general idea. Okay. The question then would be, well, right now I have it proportional, but how do we know it's not like area squared or distance cubed or something, right? Like we have kind of the general idea, but we don't know the exact nature. Right? It turns out it is proportional. Okay, so this is actually truly the relationship. It's not like area squared or distance cubed or something. Okay. And we have enough now that we could actually just math it out. Ready for it? Because what I said was, let's relate the capacitance to geometric quantities. Now we have the geometric quantities, the area and the plate spacing. Qualitative. Let's be quantitative. Okay, yeah. So, you want me to write it, or do you want me to just click a button? Okay, click a button. You're like, oh, okay. Sometimes, so it's weird, like when I used to do it all by just button clicking, and people said it felt impersonal, like I wasn't working hard. So then I went to writing, and they said, oh, we can't read that. Can you just do button clicking instead? Okay, well, okay. So, trust me, I'm working hard, okay? It's for your viewing purposes. Okay? So, I'm going to start off with this. So, two reminders. First of all, for a parallel plate capacitor, we have sigma over epsilon naught. I've written it on like 3 slides. The second thing that I'm going to highlight here is that the change in potential is essentially the electric field times the distance between the plates. That's essentially doing I mean, we say that, hey, the electric field is the potential divided by the distance. I've just moved the distance over to the other side. Just the starting point. I'm going to start off with this top one. I'm pretty sure.
What does it mean by change in distance?
I'm sorry?
Oh, sorry, what does it mean by change in distance?
Change in distance, for the purposes that I'm thinking of here, it's the distance from the bottom plate to the top plate. So the separation distance, D.
But does it mean that it has to change every time, or is that?
No, it's, it would be what I call, no, that's a good question. It should be a relative position vector. Two different locations at the same time. So I have point A, I have point B. I mean delta R to represent the distance between those 2 points.
Is the distance between two plates or the distance that one plate is moved?
Yeah, no, it's the distance between the 2 plates, okay? Yeah, I'm done like, taking a capacitor and stretching it, or taking a capacitor and increasing the plate separation. Yeah, that was just to get us to the proportional to area, inversely proportional to distance. So yeah, I'm not changing, so now, boom, I've got a capacitor in front of us. I'm not changing that, we're not doing anything fancy there. So I believe that I start off with this top equation, and I'm going to substitute in the definition of sigma. In other words, the charge on the capacitor plate divided by the area of the capacitor plate. Yeah, there we go. This is where I get in trouble, because if I'm writing it out, I know exactly what comes next. Whereas if I click through it, then I don't. Yeah, okay, so I said I'm going to start off with the top plate. Guess what? I'm starting off with the bottom equation instead. So the change in potential, we could write it as the magnitude of the electric field times the plate separation. So I'll just write that in. And this bottom equation, all I've done now is taken the definition of the electric field for a parallel plate capacitor, and I've substituted it in for the magnitude of the electric field. So we get the idea that the change in potential from one capacitor plate to the other is the charge density on the plate times the plate separation divided by this constant epsilon naught. I know what I would do next if I'm writing it out on paper, so I think this is what I would do next. Is this okay so far? Just using the 2 relationships that we've already dealt with. Slope and the parallel plate capacitor strength. Now up here, I think I start again, I hope, with the definition of capacitance. I'll click, hopefully, yes, I got one! Yes! So now I've got an expression for the change in potential between capacitor plates. And I've got a definition, I've got the, how I've defined the capacitance. I'm going to take this and plug it in for delta V right here. Just going to take that expression and substitute it in. Yeah, okay, good. And notice, because you're dividing by a fraction, you get this compound fraction, and so I just flipped it so I don't have the compound fraction anymore. Now let's substitute in the definition of sigma. We said sigma is the total charge divided by the area. So we're going to substitute that in right here. You don't have to wait for me to click through it. You can do it, right? Just go ahead, plug in sigma, charge per unit area. I mean, I can click through it too, yeah. There's a writing, I mean, I feel bad, like, you guys are writing furiously. It's always the pacing that's the problem, right? I can just do this one.
Coulombs of charge?
I'm sorry?
Coulombs of charge?
Yeah, the units of sigma would be coulombs per meter squared. So total charge divided by total area. Oops. So all I've done here is sigma. I've plugged in charge per area. And because it's in the denominator, I've just, flipped it. Again, to avoid the compound fraction. And here we dance a little jig. We say, oh, goody, goody, because you notice something. What happens to the Q's? They cancel out. Remember I said that, hey, this doesn't depend on the charge. It doesn't depend on any of that stuff. It depends on the physical shape of the capacitor. Which means the charges should cancel out at some point. All right, so the charges here cancel out right here and here. And here is an expression. I'll emphasize this is for a parallel plate capacitor. Plate capacitor. And part of the reason for that is we started off, this expression is the electric field for a parallel plate capacitor. So at the end of the day, this only applies to a parallel plate capacitor. So, for example, you want to make your own capacitor. I say, awesome. You say, what should I make it out of? I say, I don't know. You can use 2 quarters. Right? Take 2 quarters, put them really close together and charge them up. Boom, you've got a capacitor. Say, well, what's the capacitance of this? How much charge, what's the capacitance, area of the quarter, and the separation distance? You can find it out. Yeah.
So I just want to make sure I'm getting this right. So for area, it's the area of like the whole entire plate, correct? And
Yeah.
not like the distance between the plates.
Yes, correct. A represents the area of the plate that you're using.
Okay.
D is how far apart the plates are.
Okay, it wasn't like the area.
It's not the, I'm sorry, the area of the,
Yeah, I was just saying it's not the area between the plates.
correct, yes, that's correct. It is not the area between the plates. So we'll play around with that. From a practical matter, so if you wanted to make a parallel plate capacitor with quarters, from a practical matter, it's really hard to get the quarters close together without touching. So usually what ends up happening is you put some material between the quarters that doesn't allow, that you put some sort of insulator between the 2 quarters. So as you charge up, as you cause a charge separation, the charge can't move easily from one coin to the other. Right? You put some barrier in between the 2 that prevent it from moving. And that's really where you blow up a capacitor, is that you put so much charge onto the plates that that insulator all of a sudden becomes conducting. And then you arc, and then you've destroyed your capacitor. Insulators, unfortunately, will conduct electricity, so long as you put a high enough potential difference across it. The canonical example is air. Air is a really good insulator, unless you have a nice storm cloud overhead that's at a really high potential. And oh, by the way, usually we refer to the potential, the electric potential of the ground as 0, otherwise called ground. And if you get high enough electric potential in the cloud top, all of a sudden air becomes conducting. Which is a bad day. Well, maybe not a bad day. It's a nice day to sit on the porch and watch. Right? Not play golf. Yay, nay. So again, we get that it's proportional to the area, it's inversely proportional to the separation distance. You can play like the what if game. shoot, yeah, so we played this game where we put a set amount of charge on, and then we, altered the dimensions of the capacitor to see what happens. You can play the other game. You could say, let me set the potential difference between the plates, and then play around with the stretching. Right? So I'll leave that for you to think about. We'll start there on Friday. But imagine for a second that you put a constant potential difference across the plates, and you decide to increase the area. What happens? Or the same thing, if you put a constant potential difference between the plates, but then you pull them apart. And to help phrase that, we looked at a constant charge and asked ourselves what happens to the potential difference. Now I'm saying while you're eating lunch, think about a constant potential difference and ask yourself what happens to the charge on the plates. Okay. Cool, hey, I'll see you Friday. Thanks for your attention. We'll pick up there on Friday.